In this video, we are going to demonstrate how to perform kinetics simulations in MatCalc in which the growth of matrix grains is also accounted for. With this feature, the MatCalc simulations can be applied for the design of the heat treatments for the optimal grain structure of the material.
Create new workspace. This can be done with a click on the New Workspace button at the top of the recently used workspaces. Next, read the data from the databases. In Menu Global, click on Databases. In the new window, select MCFETDB database from the drop-down list. If it is not present there, click on X button followed by clicking on Open button. Then, select the database and click on Open button. Select carbon and niobium from the elements list. On the phases list, select BCCA2, FCCA1, liquid and cementite. Click on Read button to read the thermodynamic data. Next, select diffusion data on the left and click on Read button again. Select MCFETDB database on the list and click on Open button. Close this window by clicking on Close button. A quick review of the phase summary window reveals that an additional phase FCC A1-01 was created by MatCalc, next to the 4 ones that were selected from the database. In Phase Details window, the composition of this phase is given, which corresponds to the niobium carbide phase. In Menu Global, click on Composition. In the new window, select Weight % on the bottom. The in % box should be checked. Next, enter 0,1 for carbon and niobium contents. Close this window by clicking on OK button. In Menu Calc, click on Set Start Values to obtain initial phase fraction values. Next, click on the equilibrium icon and click on Go to find the thermodynamic equilibrium for the system at 1000 degrees Celsius. The result in phase summary window shows that 2 phases are in equilibrium at this temperature, FCCA1 and FCCA1-01. The values of phase compositions displayed in Phase Details window reveal that the former phase represents austenite, while the latter represents niobium carbide. Click on Stepped Calculation icon to open the Step Equilibrium window. The default settings define the calculation between 400 and 1600 degrees C with a step of 25 degrees Celsius. Click on Go button. Next, click on Create No Window icon, switch to the User Defined tab. Select the third item on the list 01 All Phase Fractions over T Celsius Logi and click on OK. The plot window appears with the equilibrium phase fractions over the defined temperature range. This will help us in the design of the kinetic simulation. I am going to simulate a system consisting of pure austenite in the initial state. Hence, I take the start temperature of 1400 degrees Celsius. As only FCCA1 phase is at equilibrium at this temperature. Then I am going to cool it down to transform austenite to ferrite completely. The transformation will be complete under 720 to 730 degrees Celsius. During the cooling, formation of NBC is expected. As FCCA1-01 phase is stable below 1300 degrees Celsius. Finally, I am going to heat the system up to 1000 degrees Celsius and investigate the grain growth of the newly formed austenite at this temperature. Let us start with the definition of the precipitate phase. In Menu Global, click on Phase Status. In the new window, select FCCA1-01 and cementite phases from the list on the left, and click on Create button on the bottom. A window appears with a drop-down list. Select Precipitate there and click on OK. New phases FCCA1-01P0 and cementite P0 appears on the list. Select FCCA1-01P0 and click on Nucleation tab. In the Nucleation Sites area, Uncheck the box with bulk description and check the one with dislocations description. Now, we are done with the precipitate phase setup. Next, I will define the precipitation domains. In this example, 3 precipitation domains will be defined, one representing ferrite and 2 others, representing austenite at various process stages. Each domain needs a separate equilibrium phase. The BCCA2 for ferrite and FCCA1 for austenite are already available, but a second austenite precipitation domain requires a second FCCA1 phase. To create it, select FCCA1 phase on the list and click on Create button on the bottom. This time select Equilibrium on the drop-down list and click on OK. You will notice a new phase FCCA1-02 appearing on the list. Afterwards, click on OK to close the phase status window. In Menu Global, click on Precipitation Domains. Click on New button on the bottom left. A window appears, where the name of the domain phase can be typed. I will call the first domain ferrite and click on OK. Select BCCA2 phase from the drop-down list in Thermodynamic Matrix phase area. Next, click again on New button to create the next domain, which I will name as austenite_1. Select FCCA1 phase from the drop-down list in Thermodynamic Matrix phase area for this domain. This will represent the austenite matrix at the initial state. At last, create the third precipitation domain, which I will call austenite_2. For this one, the FCCA1-02 is to be taken as the thermodynamic matrix phase. This will represent the austenite matrix formed from ferrite, so a few more setting modifications will be done here. First, an initial grain diameter field type in 1E-6 representing 1 micrometer. Next, switch to MS Evolution tab and select Grain Structure tab. In the Grain Size Evolution Model drop-down list, select Single Class Model. As we are done with the precipitate domain setup, click on OK button. The last thing for the kinetic simulation is the definition of the simulated heat treatment. In Menu Global, click on Thermomech Treatments. Click on New button and name the treatment. I will name it just Treatment, confirming with a click on OK button afterwards. Then, click on New Segment button and double-click on the segment data that appeared in the data field. In the new window containing the data for the very first segment, type 1400 in the Start Temperature field. Next, set the end temperature to 720 and the cooling rate to 0,1 in the respective fields. In the precipitation domain drop-down list, select austenite 1. Click on the plus button followed by a click on Yes button to create a new segment. In the next segment, set the end temperature to 600 and the cooling rate to 0,1. This time, set ferrite as a new domain. Create the third segment, in which the end temperature will be set to 880 and the heating rate to 1. In the fourth segment, set end temperature to 1000 and keep the heating rate of 1. In this segment, set austenite 2 as the precipitation domain. Finally, in the last segment, the material will be kept isothermally. Select heat cooling rate and delta time from the drop-down list in ramp control area and set the heating rate of 0 and delta time of 30 times 60 seconds, which corresponds to 30 minutes. Click on OK button to close the segment editor. The whole treatment can be reviewed on the diagram in Preview area and the List and Data area. Click on OK to finish the heat treatment definition. To avoid confusion, remove the plot with equilibrium phase fractions before the kinetic simulation will be performed. Next, click on Microstructure Simulation icon. In the new window, select the From TM Treatment option button and select Treatment from the drop-down list nearby. Next, click on Go and confirm this decision with a click on Yes button. As this is a very simple system, the calculation proceeds quite smoothly and is completed after a few seconds. Let us visualize the results on the plots. Click on Create New Window icon. Switch to User Defined tab. Select the fourth item on the list, 03, Kinetics, 4 frames, TFNR, links, and click on OK button. The plots containing the time evolution of system temperature, precipitate phase fractions, number densities and mean radius appear in the new window. The phase fraction plot is dominated by the cementite curve appearing in the temperature range of ferrite precipitation domain. Next to it, the increase in niobium carbide phase fraction during the isothermal holding at 1000 degrees Celsius can be also observed. The plot of precipitate number densities shows that the precipitation of niobium carbide occurred already in austenite during cooling, but a further nucleation wave is observed in ferrite, when the carbon supersaturation increases. Additional nucleation wave appears also after the cementite dissolution. The mean radius of niobium carbide precipitate at the onset of heating is around 5 nanometers. But this value increases after heating and isothermal holding to about 20 nanometers. Right-click in the plot window area and click on New Plot in the appearing menu. In Variables window, find the $austenite2 variable, which is located in Prec domain struct SC variable group, in the $d section. Drag and drop this variable on the newly created plot. The variable value stays at 1 micrometer for the simulation time when this domain was not active, but rises sharply to about 120 micrometers, when a grain growth seems to be stopped. For clarity, adjust the y-axis settings. Click on the y-axis on the grain diameter plot. In Window Options window, set the scaling factor to 1:6 and change the title to Grain Diameter, Micrometer. The Greek letter mu present in the micrometer abbreviation can be introduced by typing the HTML code $mu, semicolon following an HTML tag. For a better recognition of precipitate pinning effect on the grain growth, perform another simulation in the system, with the negligible niobium content. Right-click on the plot window area and click on Duplicate, and lock all series in the menu. Next, in Menu Global, click on Composition. Set niobium content to 1E-6 and close this window with a click on OK button. Afterwards, click on Microstructure Simulation icon and click on Go. In the new window, confirm your decision with a click on Yes button. Additional curves appear on the plots, as the simulation progress. It can be noticed that the niobium carbide precipitate does not occur in this system, and the austenite grain growth rises over 350 micrometers at the end of the simulation.
You can learn more about how to work with MatCalc by viewing other example videos.
Thanks for watching.